Graph plotting. What is it exactly that makes it so bothersome? We all know what it entails. On a piece of graph paper, you draw in your vertical and horizontal axis, followed by a bunch of data values in a table to match your y and x-axis respectively. The axis can then be subdivided into regular intervals. This allows your coordinates to be plotted in, after which they can be joined up with a smooth line to form your graph. By extending the line to the y-axis, you now have a y-intercept value to read off. As for the gradient, it can be derived from the steepness of any 2 points on the graph. And that's it for straight lines. There are only 2 values worth finding, the y-intercept and the gradient, so we are pretty much done here. Given the linear equation of graphs, your y and x values are described by the vertical and horizontal axis respectively. The y-intercept value corresponds to c, and the gradient value corresponds to m. But if life was so easy, there wouldn't be a need for this video. What actually happens when you plot the graph? For a start, plotting the axis, table, and setting the scale could take up to 5 minutes of your life. If that task didn't bore you out, the next one might, looking at each coordinate and pinning them onto your graph. And if it's not your day, guess what? Connect the dots, extend to your y-axis, only to find out that you have run out of space. Stuff like this can really make you lose your cool. All that time wasted for nothing makes you want to send the whole thing up in flames. But what if there were ways to avoid such wasted effort and pitfalls? For a start, let's observe this awful scale. The x-axis is marked in intervals of 3 and the y-axis is marked in intervals of 7. If I have a coordinate 0.2, -6, it's difficult to align it on the x-axis. Likewise, no precise alignment for -6 on the y-axis either. Hence, multiples of 2 or 5 are your best bets for graph plotting. Most data values will fit in nicely along the line, which eventually speeds up the plotting process. When it comes to drawing axes, most people like to start at the edge. Don't do that. Where possible, count approximately 2 to 3 big squares away from the corner for both axes. That way, you give yourself some breathing space if the points extend to a negative y or x intercept. Most students start their origin at the corner because they are worried that their graph will be too small. But more often than not, that doesn't happen with an appropriate scale. Also, a small graph is still better than no graph at all. This is your table. In this column, the coordinates of your first point, which is plotted here. This is your second coordinate, which is plotted here on the graph. Then, your third coordinate, now plotted here. At this point, you should be seeing a pattern. This constant back and forth flipping is really slowing you down. Having to constantly refocus is exhausting, and mistakes are bound to set in when you're fatigued. Why not keep everything on the same page instead? Sure, it might look cluttered with a table, working, and graph all clumped together, but what matters is that come big brain time, you have all the numbers under your nose to minimize transference errors. Sometimes, erroneous data values are intentionally planted in a question. The idea here is to raise suspicion within you and for you to counter-propose a correct value instead. So, how does this work? To recap, the x-axis is known as the independent variable, while the y-axis is a dependent variable. This means that all y-axis values rely on the existence of the x-axis value. So, if an error exists, the independent variable should not change. The y-axis value, being reliant on x, should be the one to be amended. See this y-axis? Name it as such. The x-axis? Label that too. Same goes for the equation of the curve. When you read your y-intercept, that as well. If you're finding the gradient, label both coordinates and show how the numbers lead to your gradient value. If tasked to read off values from your line, label both the independent and dependent variables too. Because the whole purpose of graph plotting is to assess your skills in analyzing data values, seriously, just label everything in your path. And that brings us to our last tip. How precisely can you read off your data values? If your point lies along a vertical line, like in this case, the 8th out of 10 lines between 0.5 and 1 is 0.9. But what if your point lies in between two lines? Over here, right between 2.3 and 2.4. In such cases, it doesn't matter how superior your eyesight is. The highest precision will always be halfway in between, which in this case is 2.35. We've covered quite a fair bit today. To summarize, plot your scale in multiples of 2 or 5. Keep the origin away from the corner of the graph. Write all working on the same page. Rectify only the dependent variable if asked. Label everything you see, and bear in mind the limits of your precision. Even with the technology of graph plotting software, such primitive tasks will unfortunately still be around for a while. But with these tips, perhaps graph plotting may be less painful than you think.